Okay, so welcome back to the main room, everyone. So we are very happy Professor Eric has joined us. So yeah, we can start. Professor Eric, please.
Thank you very much. And I really want to say I'm terribly sorry to everyone for being late. It's not good. Okay, let's go on. So you heard yesterday my broad introduction, and then you heard others speak about inference. And often what we use for inference is to do regression. Usually it means that we have a function that we want to fit to some data, and the function has some parameters, and we want to find the best fit. But there's also another approach that doesn't have a global function, and it's sometimes called non-parametric or local regression. So I'm going to cover both of them, both the traditional and the one that follows the data. Let the data speak for itself. Okay, so I will start talking about parametric regression. Much of this is classic results that this is material that is taught to undergraduates in statistics classes, including least squares method and maximum likelihood estimation. And you heard about likelihood from Tree and others. And then I will go and talk a little bit about things like splines and Gaussian processes regression. That's local non-parametric or semi-parametric regression. Okay, so one question is, which one do I use? Okay, and when do I use regression at all? And astronomers tend not to ask this question enough, so they tend to use regression too much, I think, sometimes. But it's a broad class of statistical methods that estimate the relationships between one dependent variable called the response variable, we call it Y, and one or even many other variables, could be called covariates. And so it addresses the problem of modeling where the functional form is pre-specified. You know it. Either you know it because you are an astrophysicist and you have an astrophysical model, or you know it because, well, you don't really know it, but you're just going to choose a linear function or a polynomial or an exponential or something that you sort of think is pretty good function and it has some free parameters, and you'll test at the end whether it works. I call that sometimes heuristic. Heuristic means you sort of are guessing this is the right function. Okay. So when you have log variables, a linear fit is a power law relationship. And there's lots of power laws in astronomy. But it's better, if you can, to have some astrophysical theory from physics that you are motivated physically to use. And the science question should determine what the response variable is. Now, this is interesting because sometimes the science question does. Okay, let's say you want to estimate redshifts of galaxies from photometry. So your response variable is redshift, and your covariates are various photometric variables, or colors, or something like that, maybe morphology, whatever. So you know, because your goal is to estimate redshifts. But sometimes you have maybe, let's say, make it simple, 3 variables. The metallicity of elliptical galaxies, the luminosity of elliptical galaxies, and the velocity dispersion of their stars. And it ends up those 3 variables, which don't seem to make much sense. They don't seem that they should be related to each other so much, have an extremely good regression line. I mean, they're very, very closely related to each other. It's called the fundamental plane of elliptical galaxies. But we don't really have a clear question. Do we want to predict metallicity as a function or luminosity as a function? What do we want to do? And if you don't really know, you don't have a question to ask that defines a specific response variable, then don't use regression. Use principal component analysis. Treat all 3 variables symmetrically. Or use a specialized regression like orthogonal regression that treats the variables symmetrically and does not choose one variable as special. But if you do have a special variable, because just scientifically you actually asked that question, then you want to run regression. So how would you do it? Why would you use it in astronomy? Well, there's thousands of examples. The structure of a galaxy might be an isothermal sphere, or a nonlinear model called a Sirchik model for an elliptical galaxy with a bulge. The spectrum of a source could be black body, or synchrotron, or a very complicated stellar atmosphere. Maybe you have an exoplanetary system, and then you have clear examples of Keplerian orbits. And maybe you want to predict the number of planets or the eccentricity of the planet. Maybe you're studying a galaxy, maybe our own galaxy, and you want to evaluate the dark matter distribution. Or you're a cosmologist and you want to do regression on the lambda CDM model of the expansion after inflation with dark matter and dark energy. Okay, so these are just a few examples. This just in endless numbers of them. Okay, the way the statistician writes it down is this way. And it needs some translation. So I will translate it to English what this means. The expectation, which is their fancy word for the word mean, of the response variable y, and that line there means given the independent variable x. And this is abstract. This is not a sample. This is the underlying population that y given x will be a function of x with some parameters theta. Theta could be a vector of 5 parameters or something. With random error, epsilon. Now the error is very important because the theorems underlying regression depend on what the error is. And the theorems assume, most of the time, that it is Gaussian, also called normal distribution, that the error values for each point are IID, independent and identically distributed, so they're not correlated, and they all have the same Gaussian distribution, homoscedastic, with 0 mean and variance sigma squared. And there means normal. And you've seen some of this yesterday. Note that all of the randomness is in the term. If you take away the epsilons, the y is exactly on the relationship, the function of x. So they package it so all the scatter is in epsilon. So astronomers may be using it too often if they don't have a basis for choosing a functional form. They're just making it up. Then maybe you want to do non-parametric regression. That's at the end of the talk. And if there's no basis for choosing y, then maybe you should do something that treats the variable symmetrically. Okay, let's talk about epsilon. There's reasons for epsilon that it could be maybe you have a sample of quasars and you're relating, I don't know, some emission line strength against luminosity. And maybe that actually, if you knew absolutely everything perfectly about the quasar, if you had perfect telescopes, perfect knowledge, it would still have scatter about the relation. So that's sometimes called the equation error or structural regression model. It means it's intrinsic to the objects. But then it could be that you have error from your measurement process. You just didn't get enough photons. Or you just have other sources of measurement error. In your analysis of the CCD image, you have uncertainties of various types. So these are called measurement errors, intrinsic errors and measurement errors, or both, which is quite common in astronomy. Now, interestingly, when you read a statistics paper, they don't have this slide. They just assume everything is intrinsic or measurement. They don't tell the difference. They just say scatter, error. That's because they mostly work with social scientists who don't know the source of the error. But we often do know, and we can sometimes pull these apart. Okay, so this is a very busy slide because it actually sort of says the whole thing. We'll go into some parts of this now in a little more detail. But once you choose your mathematical model, your statistical model, a function, and once you have a data set from your telescope, then you want to find the best fit parameters, the parameters for that function and that data set that minimize something, that maximize something, that just are some sort of optimization. So the classic one from Legendre, Laplace, and Gauss 200 years ago is called least squares, also L2, ordinary least squares. But you can actually maybe not minimize the sum of the square deviations, but just as the sum of the absolute value of the deviations. And it's more robust to non-Gaussian scatter and outliers. And that's a possibility. Or you could do what R.A. Fisher recommended in 1916 and the rest of his life, maximum likelihood, to maximize the likelihood, the parameters that are most likely given the data set and the function. And there is, one can state it differently, but we'll talk about this tomorrow. There's Bayesian inference, which is also based on Fisher's likelihood. One of the questions that often arises, not always, but often, is my model too simple? Or is it too complex? Or is it just right? And this is a question of complexity, and parsimony means simple, as simple as you can. So for instance, does the lambda CDM model have a W dot term or not? Are there 3 or are there 4 planets orbiting the star? Is it an isothermal sphere or an isothermal ellipsoid? How many parameters do I add? The more parameters I add, I always fit the data better. I'll always get a smaller residual least squares, and I'll always get a higher likelihood. So it's called overfitting. If you add too many parameters, you just say, oh, I'm just fitting all the noise. And so it's actually a very subtle and important question to try not to overfit, but to fit just right. And statisticians have been thinking about that question for a century, and they have some tools. One of them is called the BIC, the Bayesian Information Criterion. Another one is the AIC, the Akayiki Information Criterion. They're actually all based on the likelihood. And you would do the MLE, the maximum likelihood, for one model, and then for a more complex model, and you would compare. And if you always do a more higher likelihood for the more complex model, but you penalize it by the number of parameters. It's called penalized likelihood measures And the difference between BIC and AIC, and there's several more, is different penalties. And unfortunately, the best statisticians in the world cannot agree. Even they all have theorems and they can't agree what's the best one. But most are using the BIC. It's the most common one, has a foundation in Bayesian theory. AIC has a foundation in information theory. But you can do what you want. The other thing that's often forgotten by astronomers is after you've done your model and you found your best fit, after you've done some different model simplicity and complexity, and you've done model selection of just the right level of maximizing the BIC, you should then see whether or not it actually fits the data. Now you have only y, only one variable. So you have a list of y's that are measured. And now you have at those locations a predicted y. So you have very simple. You have two step functions, or a step function and a smooth function. And you can run the Kolmogorov-Smirnov test. Oh, I forgot. The Anderson-Darling test is more sensitive. It's similar to the Kolmogorov-Smirnov test. But it basically says for that number of points, does the model fit well enough that it's acceptable? And this is a formal test. It gives p-values, probabilities, which are always good. Non-parametric, based on a theorem. Or you can run Bootstrap for significant levels, which is actually recommended. Okay, so this was a very complex page. And now we'll sort of talk about some parts of it. So we're going to seek balance between parsimony and complexity. And that's called model selection. And there's 2 or 3. We use the reduced chi-squared, which is actually a approximation to the BIC under certain Gaussian conditions. It sometimes is good, but not always. It's better to do the likelihood directly and not use chi-squared if you can. Now, I would like to make it's not a caution, I guess it's just a strong comment. There are theorems that relate to what are called linear models that don't apply to what are called nonlinear models. But the weird thing is that statisticians define the word linear differently than we would. For us, this is a linear model. Y equals intercept plus slope times x plus epsilon. First order polynomial. A line, linear, line, linear. That's not what they mean by linear. For them, linear means it's linear in the betas. So a quadratic is a linear function for them. An exponential like this is linear. Even a sinusoid is linear for them. But if you put the betas in nonlinear sort of locations in the equation, isothermal sphere, a power law that's scaled, sinusoid with phases, a broken power law or broken linear with an additional parameter there, these are nonlinear. And for nonlinear regression, ordinary least squares is usually, well, you can still minimize the sum of the squared residual, so you can do least squares, but you don't have analytic formula for them. You have to use numerical optimization to do it. And that's okay. There's a lot of numerical optimization tools out there, and it's usually not too difficult. Maybe in high dimensions it's difficult, but it's not too difficult. But this is an academic issue that when you hear the word from statisticians, linear modeling, they actually mean a much broader class of functions than we would use. So here's some of the theorems. I'm not going to read this page. It's too boring, okay? But ordinary least squares based on 19th century theorems and one since then, since the 20th century, have all sorts of rules of homoscedasticity and no correlation. For some of the situations, you want normal distributions. For some other situations, you don't need it to be normal. It could be different, but they have to be IID in many cases and not correlated. It's very complex that different purposes have different rules underlying the theory of regression. But there's some good news inside of these theorems, okay? And this is from the middle of the 20th century. Ordinary least squares gives you the MLE, maximum likelihood estimator, when the errors are normally distributed with zero mean and sigma squared, a constant scatter across the space. That's why many scientists, social scientists, biological scientists, astroscientists are still using the old 19th century least squares method because of this theorem. It's the same result as MLE. So you don't have to think about, are you maximizing likelihood or minimizing squared residuals? Doesn't matter. You might as well do the simplest one, and OLS is often very simple to compute. Okay, now let me sort of have two slides here on a common situation in astronomy, which is not always wrong, but is sometimes implemented incorrectly. And we would call it, sometimes we call it minimized chi-squared regression. And the statistician would call it weighted regression, weighted least squares. So the point is that our data set often comes in the form of X's and Y's of measurements, real values usually, and each of them with their own measurement uncertainty. And they're different from each other for each point. They're not homoscedastic, they're heteroscedastic. But we know the variances, we actually know those numbers. Depends on the exposure time, on the aperture, I don't know, on various things that we know. Signal to noise ratios of things we measure. So that's very unusual. Most fields do not have direct measurements of their measurement errors. Now, earth sciences, some ecological science, and astroscience and physicists and physical science does, but other sciences don't. So this is not that commonly used outside of astronomy and of related fields. And here it is. This is what you minimize. You minimize y sub I minus. Now this is for a linear function, a linear model, the intercept and the slope like this. There it is. And normally, ordinary squares is just the numerator. You minimize the sum of the square residuals. But now you're weighting them by the uncertainty of the y, the variance of the y point. For each y point, its own weight. So it ends up that this is a correct model if all of the variance in y is attributable to the known measurement errors. And if these errors are normally distributed, then minimizing this quantity is in fact correct. But if you have other sources of error, for instance, the quasars have some intrinsic error, scatter, that's not in your telescope, that you don't know about. You don't know what the quasars are doing. Then the model's wrong. Now, some astronomers start adding terms in here. They start adding some systematic errors or some quasar errors, and they start fiddling around with this. Everything there is just wrong. I mean, it's not statistics at this point. You're just guessing. So it's really a good model only under limited circumstances. So this model is used too much, but mostly by my generation of astronomers. Now, the problem actually occurs even with MLE, maximum likelihood estimation. Because even with MLE, sometimes people put in all these, the scatter is due to the measurement error, and that may be wrong. Oh, this is an academic issue that the whole use of a chi-squared statistic here is wrong. It's just non-standard. It might be chi-square distributed, this quantity, but there's no guarantee at all it's chi-square distributed, because the theorems underlying that there's chi-square distribution have to do with a multinomial experiment with contingency tables of a predetermined number of categories, something completely different. It wasn't designed at all for real values. It was designed for counting experiments in bins, predetermined bins. If you divide up the bins yourself, it's not correct. The theorems that this is wrong under many situations. So be cautious about using minimum chi-squared, weighted least squares, and even simple weighted MLE. And you might want to look at an important paper by one of the early astrostatisticians, Brandon C. Kelly, an American. He was young. He was a grad student at the time. Amazing. Very important paper. So he gives a very complicated likelihood that includes measurement error and quasar error. And it treats it in a complicated way. It's likelihood based, with the possibility of priors and Bayesian inference. And he shows that his method is more accurate than many of the traditional methods that look like this, including extra terms up here or down there. So it's just a caution that treatment of measurement error is often more difficult than many astronomers think. I frankly think if the measurement errors are small compared to the intrinsic scatter or some other scatter, just forget them. Don't weight at all. Just put in epsilon. If they dominate, then you should do this model and hope the measurement errors are good. All right. But there are many, many versions of this, of regression of this type. Ordinary least squares and MLE as the basics. I just mentioned weighted regression. There's robust regression when that epsilon, the scatter, is not a Gaussian distribution with a nice peak and low tails, but has bad tails and has outliers, or it downweights or removes the outliers. This is an entire field of statistics, not just one method. It's huge. One of them is L1 regression. Then I mentioned orthogonal regression that treats this variable symmetrically. There's at least 4 different lines that can be used, and there's no theorem as to which one's best. There's nonlinear regression, where the trick is optimization. If it's high dimensions, you may not optimize, you may not get the right solution at the end because of numerical problems, not because of statistical problems. There's the possibility that the regression is discontinuous, that you have one function here and another function here and another one there. And then you have to not only find the parameters, you have to find where the change points are. There's a new, this is last 20 years, shrinkage and ridge and lasso regression, that for high dimensional multivariate problems, it actually sort of combines some L1 method with some L2 method in a complicated way to help stabilize high dimensional problems where inverting the matrix may not be possible, for example. I mentioned that I personally sort of stumbled on what to do with upper limits. There's a whole series of regressions with upper limits, censored regression. And for truncated, a flux limit, a sharp limit, no information above the limit, Tobit regression. Tobin is named after James Tobin, a Nobel Prize winner in economics. And then you don't always have to fit the mean or the median. You can fit quantiles. It's called quantile regression. It's fairly new. It's computationally difficult. But it's often a very big sample. And the scatter is not symmetrical, is not Gaussian. Maybe you go for the 10%, the 50%, and the 90%, and you see the different shapes. It's really cool. It's really cool. Just lovely stuff. So my concluding remarks is that regression is very widely used in astronomy and should be, and often is used well. It's crucial for understanding situations. We are reducing your data. You have a lot of X's and Y's, and you want something simple, a simple curve, or even just simple parameters to the function, the thetas. And maybe your science goal is just theta. But there are poor practices. I see it in the, editing that I do. We assume power laws even when things are obviously not power laws. Well, that's not a good thing. Then all the parameters you get, if the function doesn't fit the data, then the parameter values are sort of meaningless. It's called misspecified models. You may not know the response variables. It depends on your question. Sometimes we overuse minimum chi-squared because measurement errors may not be the only source of error. The model selection is often tricky. Should I choose a complicated model or a not complicated model? That's called nested, but also this model class or a completely different function over there. Let's take a continuum spectrum of a quasar. Should I use a multi-temperature black body or a synchrotron model? Completely different formulas. And yet I could fit both of them and get parameters. Which one do I want? I don't know. Oh, if I do polarization measurement, maybe I'll prefer synchrotron, but that's what that means. It might even lead me to do more observations. Astronomers are not doing enough residual analysis, looking at the differences between the observed and the predicted Y values. They should study it to see if there's extra features there or are characteristics that may be either a problem or maybe scientifically interesting. Look, I fit this, and there's something left of interest. Maybe that's the interesting science, is in the residuals. And then we'll talk about this tomorrow, that Bayesian inference in the astronomy literature is being used too often. It really is just MLE in many cases when you have very simple priors and simple problems. So that, ladies and gentlemen, is my introduction to you of regression, where regression is, there's a global formula for the whole data set. So I'll like to stop there and ask, do you have any questions? Now, I heard a little bit of the talks yesterday, but not many of them because I went to sleep. And now so I don't know everything that you heard yesterday. But maybe you want to ask questions connecting yesterday and today. I don't know. Any questions at all?
Thank you very much, Professor Eric. So we have a question here from Abdullah. Please, Abdullah, you can start.
Okay, thank you. Hi, Dr. Eric. I have two questions. The first question is about the balance between the model and the complexity. And you said that there is a question about are 3 or 4 planets orbiting around the star. And also the second question, how can I determine which variation regression that I need to use for my data?
Okay, so the model selection problem is tricky because the statisticians cannot agree to tell us to do one thing. But let's just take the BIC. So there's a paper with, I don't know, 15,000 citations or something by 2 prominent statisticians in 1995 that said, if you have model A and you have model B, and the BIC, the BIC, the Bayesian Information Criterion, is this one's more than 10 units, BIC units, better than this one, then you choose that one. It's maximum, it's better. If this one's more than 10 over that one, you choose that one. And if they're within 10 of each other, then you don't know, they're both good. They're both equally good or equally bad. And so this number 10 for significance was difficult for them to estimate, and that's the number that's recommended that we use. And cite their paper for the reference. So that's the BIC sort of decision to be made on model selection. If you're 10 units better than the other model, then you know which one to choose. Now,
So
as
I
for
need
which
to
one,
try.
I'm sorry, Abdullah, yes.
I'm sorry. Just then I need to try like more than like way of the regression, the variation of regression. I need to try more than one basically until I find the difference between them, until I find the 10 units different, right?
Right. There are other things as well. There's an old classic one that's easier to understand than the BIC is based on likelihoods. It's hard to intuitively understand it. I'll give you one that comes from ordinary least squares theory, Abdullah. It's called R squared. It's just the sum of the squared residuals. It's a variance. And it's normalized to the original variance. So maybe you have a data set and you fit a model to it. And you say, okay, the original variance was 43, I don't know, flux units squared. It's a square thing because it's variance, it's squared. That was the original, was 43 units. And then you say, oh, after I fit it, it's down to 20. That means I only, a little more than half of the variance was fit by my model. I don't know. I don't think that's so impressive. Now I fit another model. I got the sum of square residuals divided by the variance down to 10%. That means 90% of the variance is in the model. Yay! I did a lot. So I actually think astronomers should be quoting R squared often. What's the variance before, the ratio of the variance before and after, or after divided by before the model. And if you account for 90% of the structure, then your reader says, oh, Abdullah, you have a model there. You took 90% of the structure out, you're left with some Gaussian white noise. It's a pretty good model. And then the BIC helps you decide between two models. This model and another model, either more complex or simpler, or even a totally different model. So these are called goodness of fit measures and model selection measures, residual analysis of various types, graphical and others. All of these are things you do after you do the fit. And astronomers are often very good at fitting, but they don't do enough afterwards to check it out, to tell us, the reader, more. You show us a residual plot. And then you say, oh, nice, small, clean residuals. Good function, good fit. Tested alternative models. BIC is definitely better than the others. Then you just feel better. Abdullah did a great job fitting his data. If you just guess a function, fit it, and take the parameters and run, I'm not so sure. Slow down. That's my advice.
Okay, thank you.
Okay, thank you. Now, Rafi, you can start your question.
Am I audible?
Yes.
Yes. Thank you. So I tried to fit the model previously, just a test that I a model of AGN, a broadline emission region in AGN, from an AGN. So the it was LMFit package in Python, and they showed four values like chi-squared value, reduced chi-square, IKK information criterion, and Bayesian information criterion.
I'm sorry,
So
I missed it. The Akaike
yes,
information criteria. Yeah.
yes. These four values. So you're saying that the chi-square value is not to be trusted, like
No, it could be good. It could be fine. In fact, take a look at that reduced chi-squared. If it is 1.0 or very close to 1.0, then the model fits the data and the assumptions of the model are right. The measurement errors correspond to the true scatter. So the reduced chi-squared helps decide that your model was a good model for weighted least squares. The AIC value itself is often some crazy number. You can't even, it could be negative, it could be 1,000,000, it could be anything. It's almost useless. The only thing is the difference between two AIC numbers. That's the only thing that's useful.
thank you. Thank you.
Okay, I think I'll go ahead and finish my
Okay, please.
and tell you about something that it's actually not usually called regression by astronomers. It's called smoothing the data. Okay. So what should we do when we do not have a meaningful functional model from astrophysical theory? And maybe a simple power law or some linear or something gives a poor fit to the data. It has some structure in it. In this case, which is very common in astronomy, statisticians recommend non-parametric regression that fits the data with simple models like a parabola or something, but only locally, and moves along the data set and keeps on fitting them for parabolas or cubics or something without having a formula for the whole thing. It actually has lots of little formulas. That's why it's called semi-parametric. There's actually a lot of formulas in it, but they're sort of useless. It's too complicated. Okay. So and it's based on something called density estimation, which we call smoothing the data. So I have to give a couple slides on smoothing, and then I'll do non-parametric regression. Oops. Okay. So the most common one of just smoothing let's say just one variable, could be done in multiple variables, but it's done at low dimensions, is to just convolve it with a kernel function. It's called kernel density estimation. Density means like PDF, probability density estimation. So the kernel is usually a Gaussian. It's perfectly good. Actually, theoretically, it's better to use an inverted parabola, an upside down parabola called Ipanechnikov kernel. Okay. And a square kernel, boxcar, sometimes called uniform kernel, is actually not as good. Okay. It's better to use a smoother kernel. But the hard part is to choose how thick, how wide, or how narrow the kernel should be. And statisticians have thought a great deal about this. And they recommend that you choose a smoothing window that minimizes something that looks like least squares. It says that the kernel estimator, the little hat there means estimator, kernel estimator, minus the original data, quantity squared, integrated over the whole thing, and you minimize that. And some mathematics tells you that it's equal to the bias squared plus the variance. So some astronomers say, oh, I just want to minimize the variance, but they don't recommend that. If you go for the smallest possible variance, the lowest noise, okay, then you'll end up with too wide a bandwidth, and it will have high bias and missed details. If you choose too narrow a kernel, and you'll follow the data closely, small bias, but you'll have high variance. So they want it just right in between, okay? And there's a method called cross-validation, which is a Monte Carlo procedure similar to the bootstrap that helps you choose this Mies bandwidth. So here's just an example. The true data is the gray curve. It's just a Gaussian. Here's the data underneath. It's just Gaussian data. Looks like about 100 points. And here's the red curve. Too many wiggles. H, the width is too small. Here's the green curve. Too few wiggles. H is too big. And the minimum Mies gives the black curve, which is pretty close to the gray curve. Not perfect, but it's certainly pretty good. Okay, so now let's go back to the regression problem. The regression problem is where we have y, x and y, okay? Estimate y is a function of x, okay? So we're now going to talk about kernel regression. And here it is. It was written down by two different statisticians in 1962. It's the kernel smoother of x's times y divided by, normalized by the kernel, the sum of the kernels. And you just go along and you do this for all the x's. So here's a little diagram from Wikipedia of this method. Here's the inverted parabola, could be a Gaussian. We're going to evaluate it at this location here. We're going to take each one of the points inside of the window, this little parabola. This is h, the width. And we're going to weight it by this parabola or Gaussian, whatever it is. And we're going to get a value here. So the true function is green. It's a sinusoid. The data points are data with the true function with Gaussian noise. And the red function is the estimator from kernel regression. And look at that. It actually did very close to the green. Pretty good. Using the Mies, the best chosen width. Did a good job. There's others. This one fits a parabola locally inside the kernel. And another one of, excuse me. And it has, it's called Loess, and one that involves likelihoods. And there's actually an MLE is called Kriging. And it has another name called Gaussian processes regression, where you have flexibility in choosing this kernel, not just a parabola or a Gaussian, but it could have additional structure in it with parameters that you actually estimate along with the curve. So Kriging or GP regression is computationally complex. It's a n cubed for n points operation computation, because it's simultaneously trying to figure out the kernel and it's trying to figure out the curve. And it does it back and forth and back and forth. It's very complicated, but it actually is okay. But it still assumes Gaussianity. And there's another one. This was the oldest one, 1940s and 50s, called splines. And they generally fit cubics as you go along. And it was one of the most important applied mathematics papers of the 20th century, was how to make the cubics all smoothly fit together. And once they figured that out, then splines were very popular. But then they lost interest because you have to specify in advance where to calculate it. And if you choose too few knots, they're called, where you calculate the splines, then you miss some structure sometimes. But if you choose them perfectly, they're really good, but you don't know how to choose it perfectly. So this has actually been worked on more recently. And there's new likelihood-based ways of choosing the knots for splines. And this makes splines attractive again. They were very attractive in the 1950s, 60s, and 70s. It's all they had, but before they had computers, were splines. And then people dropped it in favor of Loess and Kriging. And now people are going back to splines because there's new ways of choosing knots that are sophisticated, such as Robert Cass's way. So there's a large literature on this, and here's just an example. One of my favorite books is called Local Regression and Likelihood by Clive Loader, and he describes every page how to use his package in R in CRAN. It's called LockFit, Local Fitter. It's a brilliant package. It deals with stochastic measurement errors, deals with censoring and upper limits, deals with uneven spacings. It's just amazingly flexible. It's brilliant. All with solid mathematics. This book is a review by Takazawa, a Japanese statistician. And here's one from economics. Here's one on Kriging from geology. And here's a new one with cookbook in R of other methods. These are top statisticians. So, comments at the end? Due to unfamiliarity with kernel density estimation and non-parametric regression, except some people know GP regression, but they don't know the others. Astronomers, I find, are too often fitting their data with simple power laws or a power law with a threshold or something heuristic. And unless there's some scientific reason, maybe we should let the data speak for themselves and estimate a smooth distribution non-parametrically. And it often is useful. Sometimes you actually want that slope. For some reason, you want the slope value, even if it doesn't fit too well. But please understand, it's not that meaningful if it didn't fit well. So it's not clear whether you really want to use it for science. And there is confidence intervals and bootstrap errors on some of these methods as well. Of non-parametric regression, just like there is for parametric regression.
Okay.
So,
more question session, Professor Eric. Okay, here we have Fisa. Please, you can ask your question.
It's a good morning for me. Hi, sir. Thank you for the great lecture, sir. So I have this doubt, like when we do the local estimation of the curve, like if you are trying to fit a light curve of a binary cell or something, how can we estimate the period or anything from the light curve if we are fitting locally? Like if you're fitting a local function continuously, how can we estimate a period or something like that from the fit?
okay, so period search is a different topic. It's another lecture. It can be quite difficult, particularly for sparse, irregularly spaced data, light curves that we often have because our telescopes, the sun comes up, we can't observe, and we don't get that many data points often. So the only really, really good time series that ever was produced in astronomy was the Kepler satellite. 4 years of data, evenly spaced perfectly but that's very difficult and expensive to get that. So periodicities are quite difficult to do, and it's a very tricky business. So Vaisak, let me just give you one example of why it's difficult. The Lohm-Scargill periodogram is a generalization of the Fourier periodogram from Fourier analysis, designed for irregular spacing of data. It's a generalization. It's probably mathematically correct. So you do it and you get a periodogram, which is a value for every trial period. And then you see a peak. You say, oh, it's periodic. And then comes the question, what's the significance of that peak? And I would say there are about 12 astrostatistical papers, each trying to answer that question, including by Scargill. And there's no consensus on the right way. The newest idea is something called extreme value distribution. Oh, they know the original formulas were wrong. Scargill's original formula is wrong, just completely useless, misleading. Could be wrong by a factor of 10,000. So it's very difficult. So maybe you scramble your data, you do simulations, you try things out, and you look at different periodograms, and you sweat and hope for the best. Because the mathematics of periodicities are very difficult, except under ideal conditions that would never occur. Infinite data of perfect noise, Gaussian noise, evenly spaced. We never have the right data. So the mathematics of determining whether a periodicity is real is difficult. The lone Scargill periodogram is easy. That's not hard. So this is actually, in a sense, quite a completely unsolved problem, but not a very solid problem. And it could be considered a problem in regression. You're fitting a sinusoid or fitting boxes or eclipses or something. So it's actually a difficult problem for Feisek, not easy.
Okay, so I don't know whether this question is absurd or something, but so after we fit like a local estimator, what if we use fit a period function or something to that estimated function to get the period out of it? Is that possible? I mean, I'm just shooting.
Good, but you don't know the statistics of what you're doing. You don't know probabilities. You don't know significances. You don't know what you're doing is right. You can do it exploring. I'm not sure. Thanks. I would publish it.
Yeah, got it. Thanks.
You got to remember the smoother is just estimating in between the points as well. And it assumed it's a cubic or something. And maybe that's not a good assumption. Maybe it missed something important, like an eclipse.
Yeah.
So even though it looks like a nice data set, there's a lot of friction in it.
Yes. Thanks.
Okay. I think maybe we should stop now.
But it's okay if there's any more question, we can have maybe one or two more, and then we can have a break after that. Is there any other question? No? Okay, if not, thank you very much, Professor Eric. It is very interesting lecture. So everyone, you can turn on your camera and then you can give a big applause to Professor Eric.
It's not needed. Thank you very much, though.
So thank you very much, Professor Eric. So we will have now about 25 minutes break, yeah. And so you can come back again at 10 a.m. And don't forget to fill your attendance form.